Sorry to cut off so much animated conversation, but I'd like to introduce our lunch speaker, Sanjiv Dov, and Das, and I can't even talk, who's the William and Janice Terry Professor of Finance at Santa Clara University. Sanjiv has a distinguished background as both a practitioner and an academic, but I'm not going to talk about that. I do want to take a moment to say what brings him here at lunch today. Last spring, we ran our first crowd-sourced contest for the GCFP, where we asked people the question, what is a SIFI? The idea was to rethink what really should be the criterion for banks, but also for other kinds of financial institutions. We got a lot of great entries. Some of the prize winners, I think, are also in the room here today. But the grand prize went to Sanjiv for some very interesting work, and he's going to talk today about that work and some extensions to it. So I'm happy to present to you, Sanjiv.
Thank you, Debbie. Make sure this is on. Can you hear me at the back? Yeah? All right, great. So I'm not only going to talk about the proposal I submitted to the GCFP, but I'll talk in general about an area of research that I've been working on related to networks in finance. Thanks, Debbie, for having me here, and thanks very much for the prize. This is joint work with several people. Right now, the most recent work, which is actually going on, is with two of my colleagues at Santa Clara, one in math and one in finance. And there's a lot of people at IBM Labs I worked with to actually build some of this. So I'll try and not block the screen as much as possible. But the talk is going to be about networks. And I'm going to do it in three phases. I'm going to talk about how do you actually map the network of the US financial system, and why do you want to do that, and what that has to do with systemic risk. Secondly, the map of the financial system is not the only thing one wants to see. One wants to actually compute systemic risk measures using that network. So that's the proposal I made, which is how do you actually compute a systemic risk measure off a network that accounts for the entire risk of the entire banking system, hopefully. And then how do you disaggregate that metric so that we know exactly how much each financial institution is contributing to the systemic risk of the banking system, so that then we can maybe arrange policy around it, or tax, or ask for extra capital based on how much your risk contribution actually is. And these are static pictures of networks that you actually get from running basic data mining and computation. Eventually, what you want is not a static network. You want a dynamic system where you can actually look ahead and say 1 year down, what's the network going to look like, and how do we actually manage the risk if it's going to evolve into dangerous territory. So that's sort of the general goal. I'll try and go, there's a lot of slides here, I won't use all of them. I'll try and generally give you a good picture of what I'm trying to do in this space. Okay, so the idea is really, some of this is a big data application, so the intersection with a lot of computer science. Of course, there's some network science involved here. Many of people in the room probably using network theory now. It's become a very popular thing with economists. Then I want to talk about how I can take Bob's 1974 paper and actually use it to drive a system of dynamic risk networks over time. Okay, so that's sort of something that's ongoing at this point in time. The two papers that are already published are here, and the third one I'm writing up, so it's in process at the point in time. If you're interested in the slides, they're here. There's a much more detailed version of this slide deck actually at this URL, and you can always download it later. Okay, so systemic risk has some basically accepted universal characteristics. We're all familiar with this. The magnitude of this risk is large, so the impact is large. It should be widespread. It's not localized. It might be big, but not widespread. That wouldn't be systemic. And finally, there's this notion of a ripple effect that you want to actually trap. And getting this ripple effect is usually done through interconnectedness, and that's why mapping a network might give you some sort of insights into how that thing might roll out through the system. My goal, of course, is to come up with a systemic risk measure, and the measure has to have two attributes. One is it should aggregate. That is, I should be able to give you a number for the entire system and track it over time so that I can see what happens. And I'll show you, I did this in India, so I actually have some data back from 2008 where we try to actually figure out what the systemic risk number is. So this is like Homeland Security. You want to say whether you're on the red zone, the orange zone, the green zone, and the regulator should sort of get some idea of how that's moving over time. And the second thing is I want to disaggregate the actual number by doing attribution. And we do this with portfolios all the time. We risk attribute, we performance attribute. So we should also be able to do systemic risk attribution as well. So I'm going to try and compute a number that disaggregates, and I can try and see which banks are contributing most to system-wide risk as well. And maybe that could then be used to designate a SIFI. There's an ongoing debate right now about whether size is important or risk is important when you designate a SIFI. And I think with the asset management firms getting into the mix as well, that's become an important thing. So maybe this is a basis for actually looking at a risk-based method for designating SIFIs rather than more a size-based sort of approach to designate a SIFI. Okay, so the Dodd-Frank Act, of course, has 4 criteria for designating a SIFI: large, complex, interconnected, and critical. That is, if it goes down, causes ripple effects to various people in the economy. And so I'm just going to put that up there and then move on as quickly as I can. Okay? What is systemic analysis? Systemic analysis is a measurement and analysis of relationships across entities, trying to understand the impact of these relationships on the system as a whole. Okay? So that's sort of the idea. And generally, the challenge here is you can't really sample anymore. So if you're trying to sort of come up with a system-wide measure, it's very difficult to find out behavior attributes by just sampling subsamples, because you might miss large-scale system properties. This, in some sense, makes this a big data problem at some level. Okay, you want to get the entire system. You can't sort of drop out pieces of it because you might miss important behavior. Okay, so when I get to showing you one of the applications, you'll see that it is a fairly large big data problem that needs a fair amount of computer science. What I've discovered later, of course, is that we can actually get around this problem as well by looking at sort of proxies. And that's where the Merton model actually comes in to become a proxy for much of this. Okay, so I'm going to talk about sort of general approaches that are there. There's a whole bunch of people, of course, have written many, many papers using stock return correlations or variations of stock return correlations to try and get interconnectedness. And there's a nice recent literature on this. There's the expected shortfall literature, there's the Kovar people, there's Andrew Lowe's Granger approach, which I've used in India. And then Mark here has the absorption ratio as well as another way to measure sort of the systemic risk. So there's plenty of people who have actually done this. One of the applications I'll show you is completely different. It uses completely semi-structured textual archival data from loan documents, which are public record at the SEC and FDIC, to actually construct co-lending networks for the US banking system. And I'll show you that as well. Okay? So that's a paper we did way back. And then I'm going to sort of talk a little bit more about recent work that deals with credit and network information being combined to create this aggregate system measure that's decomposable into entity-wide, entity-based measurement. So here's just a quick picture. This is from Andrew Lowe's paper in 2012 in the JFE. Andrew did a Granger causality method. So the big problem is, of course, when you start out, you want to construct a network. And you've got many, many different ways of constructing the network first before you actually do calculations on the network. So I'll do this in 2 phases. I'll show you a little bit of networks. And I'll talk about different metrics, very basic metrics that people like to compute on the networks. And then I'll show you what those numbers actually look like for the US. And you get some idea what it looks like. Okay, so Andrew looked at different types of entities, hedge funds, insurance companies, brokers, banks, and so on, and basically used pairwise Granger regressions of stock returns series on the other. Okay, so if one Granger causes the other, then there's an arrow pointing at the network from one firm to the next, otherwise not, and it goes in both directions if necessary. What we want to get from these things is, what do these networks actually look like, and can we just look at the network and get some idea of what the risk might be in the system? So the Ebola network's another one that's very popular. People map it a lot. And one of the key features of these networks is risk generally spreads by going to a node or a hub, and from there actually generally tends to emanate and infect a whole bunch of other entities as well. So we want to know whether our US banking system looks like an Ebola network, like an HIV network, like, what sort of network does it look like? And so there are 2 broad types of networks graph theorists generally look at. One is called a random network, where you put down nodes, and then the connections between nodes are randomly formed. They're not formed in any particular way. On the other hand, the other categorical type is the scale-free network. In a scale-free network is usually a hub and spoke type, but what happens is the bigger nodes generally tend to attract more activity over time, and so it gets more and more concentrated in a few nodes. And that's usually what we see with social networks, for example. Powerful people generally tend to attract more and more connections, and the others don't. And it's curious, of course, we are curious to know which one of these the banking system in the US falls under as well. The distribution of node connections here, so for example, this node here has 3 connections. The dark ones there are 5 or 6. That's just the degree of each node. And because every node is an observation, we can get a distribution of this degree. And usually the distribution of those types of networks tends to be power law type. whereas the distribution here generally tends to be Gaussian. So another good example is the traffic networks. So this is the highway network in the US, generally tends to be a random network type, and then the airport network, which is hub and spoke, generally tends to be a scale-free network. Okay, so these are sort of common notions that network theorists have. And the scale-free network, of course, has advantages because it allows transmission of people very quickly through the network. So information networks generally are good that way because if they have a huge hub and spoke, information gets transmitted quickly. A Facebook network also has quick transmission because there are a lot of people who are very important in the network, and all we need is send information through those nodes, and it proliferates. Now, in finance, that may not be a good thing because you don't want to have too many hubs where disease can percolate through the system very rapidly. So we just want to know what that looks like. So once we have a network, we might want to do some computations on it. First of all, we want to know whether it's of this type or that type, which is something we're curious about. The second thing we want to know is whether who's important in the network, which banks are important in the banking network, and we use centrality, which is an old concept. Phil Bonasich at UCLA came up with this idea long ago. You basically construct a matrix that represents the network. So this is just A, B, and C, and A is obviously the most important because he connects to both B and C don't. And you can represent them as ones and zeros in an adjacency matrix, which just tells you who's connected to who. And Phil noticed that if somebody has influence X, then the influence of that person is a function of everybody else they're connected to and their influence, and who this matrix A or the adjacency tells you who you're connected to. So you derive influence through other people's influence as well, and the whole thing is circular. And to unwrap that circularity, all you need to do is basically get the principal eigenvector of this matrix, and that is your centrality score matrix. Okay, so this is what's been done. Economists are doing it ad infinitum now in unwrapping these, and we'll try and compute the centrality scores for various banks in the US system as well once we have the network so we can understand what that is. Okay? Google, of course, did the same thing. So the PageRank algorithm is a variation on this as well, but it's just more famous than Phil's work back in 1987. So, you know, so Google constructs a network of web pages and who points to whom and that network, and effectively it's part of their search algorithm. All right, diameter is the other thing we want to know in a network. If a network has low diameter, disease will spread very fast because it will go from one end of the network to the other end of the network really quickly, and that's something we worry about when you think about contagion. So for example, this graph has a diameter of 2. It doesn't look like it, but basically the longest shortest distance from any node to any other node is basically just 2. Okay, and that's something we'll compute, and we'll try and take a guess at it for the US as well. Fragility. This is another computation we want to do. What we want to say is, if there's a local problem on the network, how quickly will that problem spread and become a global problem? Okay, now this is a problem that computer scientists have been working on for a long time. It's in the theory of expander graphs. And they have this simple metric called R. And all R does is takes the degree of every node, squares it, and takes the average across all the nodes. We're very familiar with the numerator here as economists because that's the Herfindahl index. And the denominator is just a normalization. We just take the average connections of all the nodes. And so we normalize it. And it turns out that the bigger this number is, the closer the graph is to the scale-free graph. And so disease will spread very quickly on those graphs as well. Okay, so we want to compute this number as well and see what that looks like. Okay, so to get quickly into this, the first thing we did was come up against the problem of how do we set up this network in the first place. Now, you can't get a network for everything in the financial system right away. So I was working with a team at IBM. This is the whole group. And this has led to a system called MIDAS. MIDAS is a financial forensic system. It sits on top of 9 academic papers and 4 patents. So it's a way of actually pulling out everything from the filings. And one of the things we did was we tried to look at different types of networks inside the financial system as well. A lot of the technology is mining the text of all the filings, SEC filings that we have, and pulling data out of it. And I'm only going to show you a small piece of it today so that you get an idea of what can be done with this thing. But by and large, what MIDAS does is we can pull out annual reports from the SEC servers, proxy statements. This is all publicly available. We pull everything out, and then we populate databases using an entity document sort of model. And the idea really here is what Google does with your data. What Google does with your data is every time you do something in their browser, they keep a track of it. And so Google basically has an entire set of tags. If you buy pet food, they tag you as a pet owner. If you buy stuff for kids, they they tag you as having kids, and it just flips a bunch of switches on you as you use it, and they keep track of a whole bunch of other things as well. We did sort of the same thing, but with a text mining algorithm to do that, and we produced a whole bunch of sort of forensic reports. So this is sort of an example. You can't see it, but it's Citicorp and all the subsidiaries, and you can mouse over on it and see basic attributes of these things. We pulled out all the loan documents and constructed a database of interbank lending, and we can actually mine that. We found errors in the data as well. For example, here's a big error and reported it back to the SEC too. So anyway, so this is sort of the data model that there was. We have documents, which are the filings. This is an entire map of all the different filings that are made by various corporate entities. And these are entities. So a company is an entity, a loan's an entity, and so on. And so the idea is to take all these documents, have an algorithm read these documents, and then basically figure out what it relates to, which entity it relates to, and then store all the pull out all the important information from there and store it. Okay, so that's what is done. In fact, this is a very interesting picture because it has each and every filing on it, and it tells you what it relates to, what sort of entity it relates to. And I think for a finance PhD student starting out a PhD, if you just want to know where all these things are and what data is available, that's kind of a useful thing as well. And it's interesting, this was constructed by a computer scientist at IBM who had no knowledge of finance, but he actually sat down for a year and figured out, what the entities were and how they mapped to different things. Anyway, so we did a limited application over here with the loans, and the first thing is when you get a loan when a bank does a loan to another one, it could be syndicated, for example. Here's an example where Schwab is borrowed from Citibank in a consortium of 12. It's an $800 million loan, and these are loans that go from 2 days to 364 days overnight. And it's a good proxy for how these banks are interconnected with each other, because they're constantly lending overnight with each other. There is no database of these loans. All that's done is 100 to 150 page Word or PDF file is uploaded to the SEC server. It sits there, and you have that as a document. You've got to pull it down, read it, pull out the important pieces from it. There's a whole bunch of entity resolution that we have to do because the word Morgan shows up for JP Morgan as well as Bob Morgan, who signs the loan document, and so on and so forth. There's plenty of neat code the IBM guys wrote to actually tease out all those differences. But effectively, we constructed a database of all the interbank lending and the flows between the banks. And if you wanted to plot those and see what they look like, so we did it for 5 years. I'm showing you 5 years. We have about 10 years of data. But we basically taken a whole bunch of loans, and we removed every interaction between a bank that was only one-off, so that we didn't have too many of these connections, but we kept the rest of it. That's 2005. Okay, so this is a picture just taking all the lending in 2005, and it's kind of interesting because you see the three big guys are sitting in between. Citigroup, JP Morgan, and Bank of America are in between, and then there's sort of these other clusters of banks that are sitting around. These are all numbers, so we've got some ID numbers for all the banks, but these banks are sort of sitting inside the center of the system. Now, if I asked you, what's the diameter of this thing, you could probably come up with a decent guess for what the diameter of this is, what the fragility of this is, what the centrality scores might be for these different banks in the system, and so on and so forth, but I'll show you what those actually are. Now, that's 2005. As we go into 2006, the network looks somewhat similar, but it's getting a little more dispersed. In 2007, the entire thing is one big clump as we go into the crisis. 2008, it becomes sparse because everybody stopped lending to each other. Okay, so it's got sparse again. And then 2009 is also pretty sparse. It hasn't yet all come back. Okay, now this is only interbank lending. This is not CDS contracts. It's not foreign exchange trading. There's a whole bunch of other things that we could also pick up and put in here. But this is just the interbank lending networks. So the question is then, what is this score for these various different things? And so I'm just showing you some data. You can see the diameter of the network was 5 in 2005, 2006, and it actually drops to 4 because there's fewer people in the network. People have dropped out from the network over time as the crisis evolved. The fragility score is 137. That is incredibly high. Okay, by and large, computer scientists believe that it's around, if it's 2 or greater, you actually have a fragile system. That is, a local effect will spread to a global effect. We were sitting at about 137. It went up to 172 for this network. Okay, so it's exorbitantly high if you just think about fragility. I'll show you what it is for India. It's a lot lower than the US banking system. And then, if you just wanted to look at that centrality score, where you pulled out who's the most important bank, who's the second most important bank, and so on, and normalized it. The normalization does something nice for us, which says that if this is a measure of how important JP Morgan is in the entire system, then number 2 is about 93% as important. Okay, so if you're just ranking people in a social network, for example, you might want a scoring like this, but this is people ranked over here. Now remember, Lehman is down here, but Lehman was not a big player in this network. If I did the CDS network and I had data for that, probably it would show up much higher as well. Okay, but these big 3 guys here, which showed up in the network, and then Deutsche is, of course, equally high, and then it sort of drops off pretty quickly. People like Wells and all are down here now, okay, at this point. Okay, so that was just to give you a quick sort of sense of why these networks are interesting, what kind of computations and metrics we might compute on the networks, what they look like, and sort of which are the banks inside this lending network. There's something sort of terribly unsatisfying about this, and that is that I don't actually have additional information on the banks that's put into the network calculation as well. I've just assumed every bank is the same. Every node is exactly the same except for their connections with each other. What I want to do is, of course, risk weight each node and then put that into the calculation as well. I also want to compute overall what a systemic risk score is. So I'm going to skip that and go straight to this one. So finally, this is a way of now taking credit information or quality information and combining it with the network information and coming up with one number for the entire financial system. And that number is S for systemic. Okay? The idea here is E is the edge matrix or the adjacency matrix. It's the matrix of all the connections that people have. That's a square matrix, n by n if you have n banks in the system. And the vector C here is a vector of credit quality, compromise, anything you want. Okay, anything that gives you a metric of the quality of the system. And all I've done is I've taken C transpose EC, so that's a scalar because this is 1 by n, n by n, n by 1. And I've taken the square root of that. Now this looks pretty familiar to people who do portfolio risk because that's sort of like having the covariance matrix of returns in here and the portfolio weights on this side, right? It looks exactly the same thing, except it's not that because what I have in here is the network matrix, and here I have a credit scoring vector or a compromise vector. That's it. There's no other change here. Now the adjacency matrix E, or the edge matrix here, is going to have 1 on the diagonals. I need that for the calculations. And then it could be 0, 1. That is, either I'm connected to a bank or I'm not connected to another bank. But I can also have numbers between 0 and 1. Okay, so there's a whole range of numbers that I could put in here as well. And this gives me a score. Now notice what happens if the credit values get worse, that is C becomes bigger. Okay, so as C becomes bigger, credit qualities are getting worse, then the systemic score is going to go up even if the network connections haven't changed. And keeping C constant, if the interconnectedness of the banks grows up, systemic risk will automatically go up. And since all the numbers in here are all positive, we are fine. We get a positive systemic score number as well. So one of the goals here was then to calculate this number over time and see what we get and also decompose it as well. Now the decomposition comes from the fact that this function is linear homogeneous in C. And that gives me an easy way to kind of decompose this for each bank. So just to give you an idea, we'll do a quick example. Here's 18 banks, I think, and there's just different credit qualities. 0 is really high quality, 1 is average, and 2 is sort of poor quality. And I'm going to take this network. It's given by this matrix. The adjacency matrix is over here. And if I compute that calculation for S, I get a score of 11.62. Now 11.62 doesn't mean anything per se. 11.62 is just a baseline number, and then you can see how that number is sort of moving over time. Okay, so that's the first thing I can do. The second thing I can do is I can actually compute the centrality scores for all these guys in the network. So for example, bank 1 is got the highest centrality score. And if I go back and look at the network, yeah, it's sitting right in the middle with a fair amount of connections. Banks 9 and 11, 13, and all are next. And so you can see they'll be probably sitting in between a whole bunch of things as well. Okay, so I can compute that. I can also compute the fragility score of this network, which is 7.94. So I can look at how likely is a local effect going to spread into a global effect. I can also compute the risk decomposition. Okay, so people who you work with VAR already know this. This is pretty common. VAR is also linear homogeneous, so I can actually figure out how each trading desk in a trading room is contributing to the VAR of the entire trading room. Likewise, using Euler's formula, because S was linear homogeneous, I know I can rewrite it as component-wise. Okay, take the first derivative with respect to C multiplied by C. And now I know that this is the risk contribution to S of the first bank, second bank, third bank, and so on, going down. and I can plot that as well. Now notice 5 was not central in the network. 5 was off in the periphery up there, but 5 had a poor credit score, and so it actually became something that was contributing much more to risk. So you could have a high risk contribution from two ways. One is you have a central position in the network, but you have very high credit quality, or you have a non-central position in the network, but your quality is bad enough that you're going to be contributing a lot to system-wide risk. Okay, so there's two different ways in which system risk could actually kick in. If you add them all up, you'll get 11.62 because it's just mathematically determined. You can also look at risk increments. So if you're a regulator and you want to say, okay, the system looks pretty safe, but I want to keep tabs on those banks that are likely to cause the system-wide risk to jump. So then I just take the system-wide risk S and I differentiate with respect to everybody's credit score and say, what happens if your credit score goes up by 1 notch? If it goes up by 1 notch, I can re-look at all the increments here and see who's contributing incrementally the most and see whether that's somebody I need to supervise. Now, risk decomposition might give you very different answers. Here, 5 was the highest and 1 was way down there because 1 had a very high credit rating. But the moment 1's credit rating falls, because it's central, its risk increment is actually very high. Okay, so there are two different ways in which you might want to actually map this. You can normalize the score by dividing by the norm of C. What that does is really tell you how much of a network effect there is, because if this is the identity matrix, then this whole thing becomes 1. And so 1.81 really tells me that the network effect is there because it's high. And if it goes up to 2, then effectively the network effect has gotten stronger and so on and so forth. So that's one of the other things we'd like to do. While talking to a few regulators in India, for example, they wanted to compute this thing called criticality. Criticality is centrality multiplied by your credit score. Okay, so that's how critical you are in the system. It's sort of already embedded in some of the other measures, but this is a simple calculation that they wanted to see, and so we actually produced criticality as well. The other thing that came up, which is kind of interesting, is because everybody's interconnected, if somebody starts causing trouble, let's say some bank takes excess risk, will that spill over to everybody else? In the sense that if regulators are going to ask me to keep capital based on my risk contribution, and if somebody else can affect my risk contribution, then I have a problem as well, right? So there might be gaming of the system through this. And to avoid that, we want to see whether this measure is actually susceptible to gaming. That is S going to be affected? Is my risk contribution going to be affected by somebody else jacking up their risk? And by and large, what this shows is if somebody jacks up their own risk contribution goes up a lot more than everybody else's. And so the measure can't really be gamed by getting other people to be contributing more capital by playing with your risk levels as well. Okay, so that's kind of a nice thing to have from the measure as well. I have a couple of slides. I used to be able to demo the system in India from here because I sent all the code back to India. Raghu Rajan was there at that time as a governor of the bank, and one of our colleagues was actually in doing the research for this. So we sent all the code. They actually implemented it. They got a software company to put all the code up. And so you could, in real time, actually see all the banks and how they were connected to each other. What I can't show you is the fact that you could mouse over here. I would just show you that bank's connections, as well as some statistics will pop up for that bank as well out here. And then, of course, you could get the risk decomposition as well. Now, validation of this is kind of hard because you really don't know how to validate something like this without having, in some sense, an ex post evaluation. And so one of the things that was good to hear was that when they saw this picture, oh yeah, we know exactly why that bank's in the middle, or we know exactly why that bank's in the middle. And so far, that's all I've got. I don't have an easy way to validate this. What I'm doing right now is pulling a whole bunch of data to try and see what that systemic risk measure is actually correlated to in the economy and so on and so forth, because at least we get some idea whether that correlates with things that make sense to us. Okay? All right, so the system in India was very nice. You could plop down which segment you wanted. There was a drop-down box. You picked insurance companies, brokers, any subset of those. Once you did that, it would show you all the registered financial institutions that met that criteria. Then you picked the ones you wanted from there. Then you'd pick what type of plot and a whole bunch of other analysis and the date you wanted. And we backfilled this to about 2008. Okay, so we had the entire thing done. And this is sort of the plot from 2008 running all the way out to now. That blue line is really the systemic risk plot that was trending as well. Okay? And it sort of coincided a lot with problems in 2012 with currencies and things of that sort as well. But it's something that a central bank regulator can actually look at. Now, the systemic risk score for India is about 15. and it sort of depends on number of banks. And fragility was only 2.91, which is a lot lower than what we were seeing with the numbers pre-crisis in the US as well. Okay, so the thing is that these are static networks. We've got a network at a point in time, but we don't have the dynamics of it. So now the idea is, how do I actually take this and make it dynamic, or at least have some dynamic features with it? Okay, so what we did was, the idea here now that we're working on is as follows. If every node in the network is a bank, and the banks have a set of assets, and those assets have some volatility, so this is mapping it to the Merton model directly. In the Merton model, you know the assets of the firm, and you know the volatility of the assets of the firm. You can derive a whole bunch of things from that. So if I have that, so if I have the stochastic process for every asset or every bank in the system, then the network is nothing but a derivative of all these stochastic processes. So it becomes a larger stochastic being that in some sense gets driven by all the individual stochastic processes that are there. And so we try and get some idea of how that actually plays out. Okay, so that's sort of the idea here. The other thing we did was we normalized the S measure by size, okay, so that we could actually do something with it. So the equity price is something that's observable. Equity vols are observable. The number of shares each entity has issued is observable, so we can get the market cap. The risk-free rate is given. I know the number of banks in the system. And A is just a vector of components that represents the assets as backed out from the Merton model. Lambda is the probability of default, which we can back out using a Merton model as well. And then E is the matrix of connections between the banks. And for that, I'm also going to use the Merton model in this example. So the idea is, if I have two banks in a Merton model, I can work out the conditional probability of default if one bank has failed. Okay, but it's just math. And that becomes the connection from one bank to the other. Okay, so if bank A defaults, and the probability of defaulting now, if bank B goes from, say, less than 1% to 15%, then 15% is the connection strength or the arrow that goes in the network from bank A to bank B, and so on. So I work out all these pairwise connections. I can put a threshold on them saying that these two banks are not really affecting each other if that number is not above a certain amount. So I can put a threshold in as well and construct my E matrix. So everything I can get over here comes out of the Merton 74 model. But because those stochastic processes are well known and well understood, the stochastic process for the entire network now can also be driven by the system of stochastic processes that we have for each bank in place. Okay? So the math is pretty straightforward. You have the same C as before, but now C is actually the asset size of the bank times the probability of default. So that gives you sort of a credit quality. The bigger the probability of default and the bigger the assets, the more critical it is to the system. So C becomes a bigger number. That's the numerator we had before, but now we normalize it by asset size and we call it R. Okay? So the previous measure was called S. This measure is called R. And the nice thing about R is it has some very nice provable properties. One of them is it's linear homogeneous in lambda still, so that we can run the decomposition like we had before. The first property is that substances partitioning of a bank into two banks does not change the system at all, system-wide risk. Okay, so you can prove that, so I won't go into this. I figured I'm at MIT, I should at least have a few equations up. Okay, so, but it's a pretty easy proof, so that's easy. The second thing is, if all the assets A are multiplied by a common factor, it should not have an effect on R as well. Okay, and that also is an easy proof. The third property is, as the banks become more connected, systemic risk should increase. That's also easy to show. And the nice thing is that you get two polar cases. One is where they're not connected at all. If they're not connected, the risk scales with the L1 norm. And if they're fully connected, it scales with the L2 norm. And so the total risk is somewhere between the value of the L1 and L2 norm. So it's got it bounded up and below as well. And finally, R is minimized by dividing the risk equally amongst the n banks, rather than putting all risk into one bank. Okay, so that's another thing you can prove. And so this might be an argument for why the too big to fail thing needs to be resolved. So if it's too big and you split it up, you actually bring down a systemic risk, at least under this metric. Okay, so that's another thing that's easy to show. So what I'll do is, rather than take more of your time, I'll quickly tell you what we did. We've started pulling all the data we can and constructing this. So I have a prototype software. I just cooked up a little bit of code for today. And you input there's some pre-processing to pull all the data for the Merton model first. Once you do that, you feed it in. So there's a file format. If you click over there, you can see the file format. You pull it up, and then you hit this button. It'll actually show you the network and show you a bunch of other properties of the network. So I'll try and run it and just show it to you. Hopefully it'll run. So I've already uploaded the file, so I don't have to do that. And then I'm just going to say compute score. So this is going to compute this whole thing, various versions of the Merton model, and gives me the network. I can also click on this tab and show the risk decomposition, and then you can mouse over and kind of see who's contributing. So this is all the banks, including asset management companies. So you have this Brazilian bank, Unibanco, which is now the highest contributor. But this is just a kludge prototype. Okay, don't read anything into this right now. Don't do any regulation based on it. This is just, I'm just trying to show you what it does. Okay. There's Prudential, Citigroup is here, I know Jure is here. So the interesting thing here is the banks are all looking at it inwardly from their point of view, what their risk is when the system is in trouble. And I'm looking at it from the point of view which bank is going to cause the system to have a problem. So there's these two pools of risk measures. There's Acharya and gang at NYU that are trying to say, if the system's in trouble, how much more capital should a bank keep individually? And this is a different view, which is which bank is going to cause a problem for the system. And I think that's probably a different way of looking at systemic risk. But that's the way Kovar looks at it. That's the way, I guess, Andrew looks at it as well as in the work he's done. Okay, then there's risk increments. This is if your credit quality drops by a bit, what happens? And that's the whole bunch of banks here as well, and so on. Okay, so you can do this. You can also, let me jump back to the slides for a bit. I'll come back to this. There's this whole discussion about including asset managers. So you can choose to include the asset managers or not in this discussion. And BlackRock, of course, is the biggest one here, as we know. The other thing is you can use this to compute incremental systemic risk capital. So let's say we've decided at this level of systemic risk, there's a certain amount of capital banks need to keep. This thing allows you to say that if the connectedness becomes higher, how much more capital should be kept because of systemic risk, everything else remaining the same. And then we can also compute VAR, because I can actually look at the joint distribution of all these banks' asset values a year out, 3 months out, 6 months out, and recompute all these statistics at the same time, and then get a distribution of the systemic risk score, and maybe look at left tail and say what probably I can and get to a certain level of systemic risk. Okay, so let me just go there. This is just a decomposition equation. I'll go back to the code. What I've done is I've just coded up something on the side here for average correlation. So let's say the correlation of the system goes up, and I want to look at what happens to the network. I can just pull this over. It's going to recompute everything, and that's the new network. Okay. If I jack it up really high, obviously everything's correlated. You're going to get a crazy network, because now everybody's causing spillovers to everybody else. If I put it back here and I say, okay, I'm only interested in risk when between two counterparties, if they're correlated less than 50%. So let me drop it down to say 40%. I'll get the network changes automatically. If I bring it up further, I'll get a slightly different network. Now the network's getting sparser because I've said instead of 50% as a cutoff correlation, I'm going to have a connection between banks only if it's 55%. And so that does that. You can do the same thing with the risk decomp. So for example, if I change this down to, let's say, 40%, it automatically changes. You can look at how much your risk decomposition is, and so on and so forth. Okay, so I'm doing a lot more work on building this up. But the idea really is that I want to host this on a server so that anybody can input their file with all the data at any time and actually just recompute and tweak these things around. Okay, so go back here. So the idea really is to be able to, in some sense, compute these things. And if you're interested, I've actually got a server that's running that you can actually play with this model yourself. So when you get the slides, if you go to that URL, you can get in there and put in your own file or use the file that I've uploaded for the current system and toggle it around to actually see what you have. The interesting thing here also is that you don't need to actually do this at the system-wide level. You could do this within a financial entity as well, because different financial entities would have correlated risks across the different business lines. You could put them together and actually look at how much the entity is affected if they get more connected with each other as well. Okay, so I'll stop there. Just to summarize, a good systemic risk measure should be able to aggregate risk across all the entities and come up with one score for the system. And then you should be able to track that score over time dynamically. Okay? Secondly, you should be able to allocate or disaggregate that risk to each entity such that it adds up. So you can actually say who's contributing the most to the risk of the entire system. Stress testing individual banks only says something about the individual bank, and it won't tell you anything about systemic risk unless you actually analyze the network. Okay, so I'm sort of just making this bold pitch for why network analysis kind of matters when we're looking at system-wide risk, because interconnectedness matters. These are actually fairly easy to construct. And the problem is there's too much choice about what network you should have. Should you be using Andrew's methodology, using Granger causality? Should be using text mining with IBM type technology to get the connections between banks? Should we be using risk metrics that the regulator has access to? For example, in centralized counterparty exchanges, everybody knows the open position, not everybody, but the regulator knows the open position. So they could actually construct this network by just looking at the open positions everybody has with each other. So in some sense, you want to capture everything. And my best bet, and this is a conjecture, is that once we have CVA computed, CVA actually is a great summary measure of counterparty exposure from one entity to the next. Once we have the CVA measures that actually are produced on a regular basis by regulators and banks, then the network of CVA actually might be the ideal network to put in here. Okay? So that gives you static picture of the network. If you want a dynamic network, you could try and use something like the Merton model, which already has a stochastic process that's well worked out, and then build everything on top of that. Build the network on top of the Merton model, build the probabilities of default and the size of these banks of the Merton model as well. And it's kind of nice to have Bob here to talk about this. So the slides are there, and thanks very much for your attention. So, yeah. Thank you, Dave. Yeah, sure, I can take questions. Yeah.
I'm sure there's many.
Bob's.
You see a way with what you have here to create an endogenous system stress test priority?
Yeah.
It seemed to me, if I understand what you showed us, that you could essentially, of all the things that could happen, and now my feeling is most of the time a bunch of people sit around the table and think of 10 or 100 cases kind of on top of it. But again, the system, there's nobody who can do what, or at least help people do what they do when they look at these things. Right. To come up with them. Is that pretty adaptable?
Yeah, it's pretty adaptable. In fact, the other side of this thing, Bob, is that when we were looking at this in India, they were worried that what if everybody sees this map and starts so you get into that as well. And, yeah. So, but to some extent, like if you have a centralized counterparty exchange, at least the regulator can know what the stresses are in the system and who's most contributing to it and so on. Yeah. So, yeah. Yeah. Yeah.
Regulators have a lot of information that's not available to everyone else. And therefore, they could use the system without understanding.
They could. Everything I've done is completely public data, and people could recreate it. Yeah. 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 In fact, I'm also concerned that if somebody starts doing, so let's say I'm actually planning to host this for the US system on a real-time basis using public data, and then everybody can look at it and see what we're getting out of it. And there'll be some feedback, I guess, at that point. Yeah, yeah. So, yeah. Yes, Jure. Yeah, yeah.
We should think about reallocating aggregate amount of regulatory capital, or maybe like a GC component based on this instead of those individuals.
Yeah, so there is a way to do this. So the thing is, what's useful here is there's already a certain amount of capital. Now, if you're going to keep some extra capital only for systemic risk, this is a decent tool for computing that extra, at least at the outset. To do all the capital allocation based on something like this might be a reach. I don't know. There's a lot of other stuff happening. Sorry? Could be. It's certainly a rank ordering of firms for siffiness, because their risk contributions gives you a direct sort, right, of the banks. So, yeah. Yeah. Yeah.
You can include a bunch of the government financial players also in this, and just see how central they are and who's potentially exposed.
That's
to
right.
it.
Yeah. Yeah.
I mean, you notably don't have the biggest bank in the U.S. in there.
Right. In fact, the biggest bank in India. So go back to India. When I looked, the State Bank of India is the big gorilla in India, and it wasn't a big contributor. And so I asked, I said, how come State Bank of India is not showing up? And they said, we know exactly why. they basically don't deal with the other banks very much. They do everything in-house, and they don't have, so interconnectedness there was not strong, and so they didn't come up as a salient. Yeah. But they were not systemic in the sense that they didn't really have trading interactions with everybody else. So, yeah. Ben?
How do you model the asset manager in the system, since the asset manager doesn't own the assets that belong to the clients?
So right now, all I've done is I've used the Merton model as is. That is, I take your equity, I take your debt, I put it into the calculation and pull it out. So that's exactly how it's done right now. I completely agree. There's probably going to be more tweaking required to fit an asset manager properly in here. But to the extent that there are connections through the Merton model, that is, if, for example, a large asset manager fails, then the probability of everybody else failing goes up dramatically, then they would be central in this system as well, in this network. Because that's the way I'm computing. I'm just taking the Merton model and computing if, say, BlackRock fails, what's the probability of everybody else failing? Because the initial prior probability is going to be very low. If I do a Bayesian update conditional on you having failed using the parameters from the Merton model, then everybody else's probability of default jumps up. And that's all I'm doing right now. I haven't sort of teased out the separate ownership types of things in there as well. But that might be sufficient because in some sense, as long as the Merton model is doing its job reasonably well, then it is telling me truly what's going to happen to somebody else if a particular asset manager goes down. And that's what I'm using to build the interconnectedness network over here. So. Yeah, John? Yeah.
You were talking about risk increments from
Right.
institutions becoming riskier.
Yeah.
It seems to me your framework also suggests you could look at the risk impacts of altering connections.
That's right. Yeah.
So taking
Yeah.
a connection out,
That's right.
strengthening a connection on.
Exactly. In fact, I have some of that. And the idea there is, let's say we are in a systemic event, and the network tells me exactly who's causing the most risk and who's causing less, and so on and so forth. I can actually use the network to say, let me quarantine this bank. I'll just take away all the connections from that bank, and does that improve the risk of the system, and so on. What if I split the bank into two? That has sort of an undetermined effect. If I take a node and I make it two nodes and I take half the connections of this node and put it here and the other half in the other one, what happens is sometimes the overall systemic risk goes up and sometimes it goes down. The reason sometimes it goes up is because the number of channels through which the risk can percolate has actually gone up now with two nodes rather than one. But because I've split it, it might also drop it as well. So that becomes indeterminate. But it's interesting because I can run the experiment by just doing that. Now, I haven't coded that in real time so that I can play with a slider or just tap on a node and say he's gone and reconfigure the network, but that's easy. Software is not a problem. That's kind of trivial to do.
I know this could go. We have a systemic risk session coming up, so some of these questions might carry over. One more question.
Okay. All right, I'll go there.
Yes, we all know that regulators are focused on stress testing individual
Yes.
banks. Are you aware whether they're looking at systemic risk in a broader context? And also, individual regulators looking at reducing systemic risk within their jurisdiction is not necessarily optimize
Correct.
systemic risk globally, right?
Yes, that's right. I have not seen anything that looks at even the computation that says here's our systemic risk and how do we get it down. And I think right now that's the best thing the regulators can do is sort of deal with individual banks and look at, but I think one of the things that could be done, of course, is we know using those 4 criteria of Dodd-Frank, roughly speaking, what are the things that make something systemically risky. All this work is doing is putting that into sort of a formal mathematical sort of framework that can then be used. So hopefully Dodd-Frank implementations will eventually lead to something like this. Maybe an organization like the OFR is the best place to do this because they actually have most of the data that would go into a calculation like that. So.
Thank you.